All of this talk of divisors and division is based on an important important theorem, I guess you can call it, called the division algorithm. So in this segment, I would like to prove to you the division algorithm. So first, let's say, what is the division algorithm? Okay. The division algorithm for any integers a and b with b greater than 0, note that a does not need to be greater than 0, just b, b greater than 0, there exists a unique pair of integers, q and r, with, and you'll see the logic behind the choice of letters there, q and r, with q, I'm sorry, with r greater than or equal to 0 and less than b, and such that a is equal to bq plus r. Now, what does this have to do with division? Well, this is written nicely because all of the numbers here, a, b, q, and r, are all integers, which is great. But if we just take this whole thing and we divide it by b, the whole equation divided by b, we get something which will look perhaps a little bit more familiar. A over b is equal to q plus r over b. And this is just a regular division problem. So if I take a divided by b, I get the quotient, hence the letter q, plus some fraction. Now, note that the fraction has to be less than 1, otherwise we didn't do the division correctly. Now, the fraction being less than 1 means that b is less than r. And that's one of our requirements here, is that that r is less than b. That's what it requires. The numerator has to be smaller than the denominator. And r has to be greater than 0, well, just because that's the choice that we make. And when we do a division problem, we're always going to get a number that is a remainder which is greater than 0. Okay. So we have this sort of interesting statement, which is basically, yes, division works. So how do we prove this? Well, you may even ask yourself, what are we even trying to prove here? Well, what we really need to prove in something like this is not so much that you can write some equation with some numbers such that a equals bq plus r, because certainly in most cases it exists, but you can give a couple examples and show, well, obviously you can write it like that. But the question is, for any integers, right here we have for any integers, and also the important thing over here, that we have this unique pair which exists. Okay, so what we have to prove is we have to prove that for any pair, there is, for any a and b, there is such a q and a r that fit this equation. And that's the interesting thing about the division algorithm. Now, the proof is not really that simple. It's a little bit complicated. It's not hard. It's just a little bit involved. So we'll go through it. So we're going to start with existence, and hopefully I don't get too frustrated with my writing utensil. Okay, so we start with existence, and the way we're going to prove existence is by this. We're going to define a set A, which is the set of all integers. Now, it's got to be an integer, you'll see why. A minus BQ, all right? Such that A minus BQ is an integer, and just we're saying we're only counting it if it is an integer. So there's A minus BQ is an integer, and a minus bq. We also are forcing it, we want it to be greater than or equal to 0. Okay, so now, interesting set. When we have this set, it's always kind of a good idea to make sure that our set has at least one thing in it, and we're going to actually need it to have at least one thing in it in a little bit here. So let's just find a number that has one thing in it. So a, we said, isn't necessarily greater than 0. So there's two possibilities. Either a is greater than or equal to 0, or a is less than 0. if A is greater than or equal to 0, then we're going to let Q equal A. Okay, so then we have A minus BQ equals A minus B A. Whoops, timeout. Hold on. I got my cases mixed up. And you can see that I got them mixed up because now I'm rotating them. All right, so I'm going to move this over here, and we'll come back to that. If A is greater than 0, this is the easy case. I forgot this was the easy case. If A is greater than 0, we let Q equal 0. Then A minus BQ is just A, which by assumption is greater than or equal to 0, and therefore A minus BQ fits all of our criteria of A and is an element of A. Okay, so there we have one element of A if A is greater than 0, and one element of big A if little a is greater than 0. Okay, on the other hand, if A is less than 0, then this is when we let Q equal A. Okay, so if Q equals A, then A minus BQ is equal to A minus BA, which is negative A times B minus 1. All right, so in that case, then negative A is negative, so negative A is positive, so we can rewrite that as the absolute value of A times B minus 1. Now, note from our original assumption, way up here, B is greater than 0. Now, since B is greater than 0, that means, and B is also an integer, so B is an integer. So the only, the first integer greater than 0 is 1, so that means that B is greater than or equal to 1, which means that B minus 1 is greater than or equal to 0. Okay, so that means that this whole, and this is also an absolute value of A is greater than or equal to 0, so that means this whole thing is greater than or equal to 0. Okay, so if that whole thing is greater than or equal to 0, then again, it is an element of A. So that means that A minus BQ is an element of A. Okay, so regardless of whether A is positive or negative or 0, we can find at least one, and there certainly are more, but we had to prove that there are at least one element of this big set A which actually exists. Okay, now that does not prove the existence we set out to prove. That only shows that our set, which we made up, has an actual element.